e-trail guide edits due to Joan Marie by October 22nd. So is this in everybody's inbox?
We could send a reminder email, I guess, Jennifer, if you would love to just maybe have like one quick reminder email that you can send in your feedback on the PDF of the trail guide.
Okay, that's great. There's going to be a walk. We're going to actually do the trail together November 6th from 9 to 11:30, and we'll meet at the boat launch. And actually, we did this once before, and it was fun. So that's a really nice thing to everybody think about doing. The next seminar is November 6th, the day of the trail guide. It's the CZO day, and it's our very own David Eisenstadt. Strategies of nutrient acquisition and temperate trees. He's going to tell us everything that he knows about trees that we need to know to understand the critical zone. Okay, then the thing that I'm most worried about, we have a delegation of Chinese critical zone scientists coming October 30 through November 3, and we really need people's help in taking care of these guys. They're here for 5 days, and they want to spend 1 day each with different faculty members. And so you apparently have already known about this. Monday they're supposed to spend with me. There's 15 of them. And Tuesday they were going to spend with either Ken or Lily. Do you know that, Lily? October 3rd. Yeah, we might want to have one Chinese student or faculty member per day, because the last group of Chinese that came through, I mean, the English was really pretty difficult, at least with a lot of them. So Roman, are you still on for that Wednesday? Daniela is also here. I know Kitty Losi is here that Monday, and then the Chinese are here that whole week. So Jennifer, we should actually have them go to all the talks, because that's something we can do with them. They should go to Kitty's talk. They should go to Daniela's talk. And I don't know. I think each PI on each day should think about it this way. Why is Dave Eisenstadt not in it? Because he never answered your email? Okay. We really need help on this. Jason said he didn't want to do it at all, but I don't think anybody should say that, because basically we need a lot of help with this. So maybe between you and Jason, you can cover some time. They want to know how to set up their own CZO. They're going to be setting up a CZO. So they want to know what the different questions are that people are asking. They want to know how we set up the CZO, what the measurements are, that sort of thing. I don't think you have to take care of them all day. You could, you know, I don't really know exactly. We'll get more questions answered, I guess, as time goes on, but we're not getting a lot of information from them. So you need to think about how you can structure your day so that it doesn't mess you totally up, gives them some of what they need, give your students some chance to talk to the Chinese and talk about what they're doing. Okay, so does everybody kind of get that? I don't know, Yuning, we should get you here that week too, if possible. Not the whole week, but 1 day that week, something. Okay. So are there questions about that other than the 100 questions? I don't know what happened with that. That got stuck in my inbox. Maybe we can. I know. We're going to have to. Well, I think they could join. I think that'd be fine. That would slow you and Daniela down. So we need to think about this. And Jennifer is going to be starting to plan it. And honestly, I think some of the students that speak Chinese are going to need your help too, because, you know, maybe they can have a block of time where they give a talk about their work, and it could be in Chinese. And the last group that came, very little English was understood by many of them. So I think having some blocks of time with the Chinese students talking about their research might be great. Well, they told us they were coming, and then they said they weren't coming, and then they told us they are coming, and then the dates have changed, and it's just been very complicated. So, and you know, maybe we can think of some things for them to do here, because they'll never have been here before. There's plenty of things that we can have them do, but we've got to make it so that they're having a good time and everybody gets to show them a little bit, and that everybody helps. Kitty Losi is going to give the ecology seminar October 30th at 4 in 107 FRB Forest Resources Building. She's the PI of the Idaho Critical Zone Observatory, so that should be good. And then Daniel Remke, who was used to be at the Berkeley Eel River CZO, she will give a seminar in geosciences October 31st at 4. So that week is just going to be hell. It's going to be Monday, the talk by Kitty, Tuesday, the talk by Danielle, and then all that week is when the whole 15 Chinese scientists are going to be here. And we'll do our best to make it easy on people. This week, you what? Well, so what social events are you planning, Dave? Every evening? We have to have something social every evening? Right. Yeah. Okay, this week, on the other hand, we are lucky enough to have our friend Diana Karwan. She's been here since Tuesday, and she was a postdoc at the Christina River CZO. So she worked in southeastern PA and in Delaware. She was actually an undergrad at the University of Michigan, which is why she's leaving tomorrow morning. She's leaving tomorrow morning. And then she got her PhD with Jim Sayers at Yale in the School of Forestry. And then she postdoced at the Christina River CZO. Now she's an assistant professor in forestry at the University of Minnesota and working on critical zone research. And one of the things she started working on was using cesium and lead isotopes, which are short timescale isotopes, to look at sediment transport. So that's one of the things that she does. She's got slides, Dave. Okay, that means you have to do one party for the Chinese for that, because that inopportune question. And then she has worked on this sediment transport on some of her work in Christina River. She got interested in the work we're looking at here with pit and mounds and tree throw. And so she started doing a little bit of measurements here, and she came up to try to work up some data that she and I had been talking about. And so she agreed to give this talk as totally a work in progress. You know, this is kind of the work we did this week, you know, what we did this summer, but what we did in the last 3 days. So does that set it up well enough for you, Diane? And she's going to try to, you know, teach you a little bit about this topic, and hopefully we can have a good conversation about where.
It's on. Okay, so as Sue mentioned, for the people out there, okay, great. So yeah, thanks Sue, and thanks everyone. As Sue said, this kind of has been, we've collected data that's been hanging on, and we totally set up this visit and me giving this seminar to facilitate doing some of the write-up for it and some of the data workup. So let's see, this is my agenda. So Sue told you a bit about my background. We will get to time scale and talking about time scale when I enter the isotope portion. I'm a hydrologist by training, so I'm the hydrologist in forest resources, and so I work with a lot of geomorphologists, but really I want to know what events do to moving sediment around. So tree throw is definitely one kind of embodiment of an event that can move and mobilize sediment and mix sediment. So this is going to be a take on tree throw at the Shale Hills Critical Zone Observatory, but with a highly chemical perspective. And very much a work in progress. So for many of you in the room, what tree throw is probably a bit of a review, right? A tree is uprooted. It's growing on the slope for some amount of time. and it can get uprooted in such a way that it brings up a root wad with it and leaving behind a pit from where that root wad was excavated. And it develops into this pit and mound style topography. That's just a little bit of a funny aside. So this all started, and I moved to Minnesota, and I was interested in tree throw and sediment mobilization dynamics. And they took me to where we had really large, like mile swaths of blowdown events in northern Minnesota in a highly forested area. And when I got there, I realized that this dynamic was not what had happened. What had happened there was snap, where they had high wind events, but the soil was not moist enough that it brought the root wad up with it, and the trees were all snapped off somewhere taller than me. And the top of the tree was off, but the root wad didn't come up and it didn't generate the pit mound topography. So we are not today talking about snap. We are talking about tree throw that generates a pit mound dynamic. So starting to get us all on the same page, thinking about what we're going to be looking at here. We have a highly chemical toolkit with my short-lived decadal scale half-life radioisotopes and Sue's chemical profiles, where we'll be looking at some depletion profiles. So these are plots of element concentration versus soil depth, and they're normalized to something that would be fully concentrated in bedrock. So we'll see depletion when something that would be a high concentration in bedrock is normalized out and less than 0. We're looking at tree throw, which is what we just defined on the previous page, not snap. We're really interested ultimately in thinking about a tree throw reoccurrence interval that would be the time between tree throws that may happen on approximately the same location. So this would be where a tree comes in, a new tree would generate up, regenerate from where that mound environment was. As well as thinking about the density of this occurrence within the shale hills catchment. And what we'll be looking at and talking about quite a bit is homogenization. So this would be mixing of that soil profile within the mound. And we'll see chemical evidence of this where we think mixing is going on after the mound has been generated. So you are all, I'm sure, familiar with the original Shale Hills CZO catchment, where there have been several profiles along planar and swale hill slopes that are on the north-facing and south-facing sides of the catchment, where a lot of chemical profiles have been developed. So I've taken short-lived radioisotope profiles at a number of these same locations, gone back in, as well as in tree mounds that were sampled in a class in 2015. So we have a lot of chemical profiles from all these locations, as well as cesium-137 and lead-210 from the ones in blue. So these depletion profiles, and Sue has had many students working on this, kind of tell a story where it looks like there are elements that would be concentrated in the bedrock, and those elements are mobilized or lost throughout the soil profile. And we see these depletion profiles lots of places throughout the Shale Hills catchment in various, our internet connection is unstable. Is that something I need to worry about? No. Okay, that's fine. I'm just gonna keep going. Yeah, all of a sudden it's gonna be game day and it's gonna be anti-Michigan things blaring, right? Because you told everyone where my BS is from. So these depletion profiles are present throughout Shale Hills. And in fact, these are the rule rather than the exception. And so a lot of what we want to set up is if this tree throw occurs, and if slowly over geologic time, this tree throw dynamic would mix up soil profiles, why do the majority of them in the catchment show this depletion trend? You can, you're the expert.
On the y-axis, and then it goes from 0 to -1, that's tau, and it's just a normalized concentration. So for example, aluminum concentration normalized for how much aluminum there is in the parent. And we can give you the equation for tau, but in essence, all you really have to know is that if the sample is the same as parent, tau will equal 0. And if it's 100% depleted, tau will equal -1. With 50% depleted, it will be -0.5. So that value 4 at the very bottom is 60 centimeters. In the air, it's back to parent what you see is that the ridge top and the southern valley floor, you see shallower soils, you know, in the higher elevations, and less depletion, but we still see depletion everywhere.
So to keep some general numbers in mind, there have been estimates in temperate forested systems that tree mounds can persist for what I, as a hydrologist, would consider a really long time. A geomorphologist that thinks on geologic timescale might not think that that 2,000-year number is as long, but to me, 2,000-year persistence of a pit mound in a temperate forest is a long time. And so there are some that suggest for similar forests, each plot of soil, a tree is going to turn over. So this is some aspect of that recurrence interval on the order of 1,000 to 3,000 years. So again, in my thinking, this is a really long time. You know, you have relatively, I would say, long soil residence times in shale hills from 12,000 to 43,000 years. And if we want to think about this as percent of a landscape surface, there have been estimates made by Gabay and others that pit and mound pairs can cover up to 40% of landscapes in temperate forested areas. Yeah.
The soil residence time for the shale hills.
That was Lynn Ma's work.
I forget, what is that? What does that refer to?
I'm gonna kick this one to Sue.
And so it's when the uranium isotopes are out of equilibrium, and it tells you like how long the particle is as a particle losing uranium to the solution phase. So it's kind of like 12,000 years residence time from the soil, from the piece of bedrock that disaggregates as it moves up and then goes up. So this is measuring material on the surface, or is this throughout the soil pit? Well, it's like think like the ridge top, you know, here's the bedrock, and then this is soil, right? So it's how much time does it take to go through that?
Yeah, Lynn Ma published that. You have the date in there, 2013.
I'm sorry.
Yeah. No, there's nothing back there. Is there whiteboard on here?
Is whether or not those numbers are just from ridge tops.
Now, the 12,000 years is the ridge top on either side. And then as you come down the slope, it goes as high as 40,000 years at the bottom.
Just because the soils are thick and
Sue's answering all the geologic questions for me. But this came, the two of us, to ask, why do we see depletion profiles, and why aren't the trees homogenizing them? And so Beth Herndon put together some of these tau plots, that show depletion for 35 profiles from around the catchment, and all but one of them showed the general trend of depletion towards the surface. So again, why do we see these depletion profiles at all if trees are homogenizing that top layer of soil over 40% of the watershed? So how do we go from this, which you see very recently in shale hills, to profiles of mounds that have been in existence for longer? We came up with 5 possible hypotheses to evaluate here. The first is that tree throw kind of happens but doesn't significantly disrupt soil profiles. So perhaps the mixing by trees is happening too shallow for the profile as a whole to look depleted. Secondly, is that tree throw homogenizes soil profiles, destroying those depletion curves, but that it's relatively rare and only occurring over a small fraction of the catchment area. Third, the time it takes to develop a depletion profile is actually less than that recurrence interval for tree throw at a given location. So to homogenize the soil, so most soils will be observed with depletion profiles because of the time scale. Fourth, the time it takes roots and fungi to grow into homogenized soil after tree throw, and then return that profile to depletion through their mobilization is shorter than the recurrence tree throw interval. And finally, fifth, trees on average are regrowing in similar locations in the catchment, and so they're always re-affecting that same location. So if we're sampling not in that 40% that's habitually undergoing tree throw, then we would see the depletion profiles because the trees are always on the same spot. Let's see. So a lot of this is based on sampling that was done in 2010, so well before the current tree throw event that I think happened around Labor Day this year. And investigating, we're using chemical profiles that were collected and analyzed from 2 pit mound pairs from 2010. So there were augurable samples taken and soil changes that were noticed throughout, for example, the wall of where soil was augured and then a trench was dug through the pit mound pair. And so there were 2 pit mound pairs taken. They were dated by one sort of method at the time, so they get referred to relatively as the new pit and the old pit, and those new old terms are relative to each other. And throughout the talk, we're going to kind of narrow down what new and old might mean in terms of number of years or decades. So the new pit mound pair was dry and sandy, light brown in color, with roots and rock fragments that were about 2 centimeters in dimension, and these were abundant throughout the augering. The old mound soil was considered deeper at about 80 centimeters deep and is characterized by a notable lack of organic matter in the surface, an A horizon that's much thinner than the pit, and a loamy texture with 10% rock fragments by volume. And it was dark brown with abundant roots. However, roots were not common below 40 centimeters. The old mound ends up being shallower, right? Yeah, the old mound is only 20 centimeters. Okay, so this is in progress. You'll see depth profiles later that old mound truncates at about 25 centimeters. The pit extends deeper, has a substantial O horizon with about 8 centimeters of organic material. An A horizon of 12 centimeters is thicker than observed elsewhere on slopes and very dark brown soil color, with very few roots below 45 centimeters within the pit. And so thinking about the schematic of a slope surface with a pit uphill of a mound and samples taken in a depth profile from the surface. There were also samples taken from the pits. Most of what we talk about today is going to focus a little bit more on the profiles going through the mound surface. Where you see the mound surface here, and this would be one of the mounds, and you see more fine-grained material in the top, a transition about 50 centimeters, and then blockier shale beneath. Field level observations. Depth refusal for the old mound is shallower by about 10 centimeters. This is interpreted, and there's other measurements to show that this mound has eroded away, and we'll keep coming back to this throughout the talk. The depth of the manganese enrichment is shallower in the old mound by 20 centimeters, and so we're using that manganese enrichment layer from Beth Herndon's work to tell us what the surface was during industrialization. Okay.
So we did all sorts of measurements on the catchment, and there's always too much manganese in the soil. And if you take counterplots for manganese, they always increase upward, and it's consistent with atmospheric deposition of manganese. And so Beth Herndon did a whole bunch of papers on this, and it looks like, based on all sorts of arguments and based on some lead isotopes, not the kind that she's going to talk about, that manganese was deposited between 1850 and 1920. So there's this manganese enrichment at the top of all the soils. And if you look at these tablets, you can see the manganese enrichment in the mound.
So we effectively.
From the mound to the pre-existing surface.
Say it again. So some of this is interpreting, right, that manganese is definitely beneath the mound surface.
That's the marker. Textual indication for that.
I've been looking at chemical indications more so than textural. But it's, and the, you see it's like an event horizon that would show up. Exactly. With sort of a field survey on the dimensions of the pit mound pairs, every dimension of the new pit and mound is larger than the old pit and mound. That's kind of the main punchline. So we're looking at changes in geometry with age that have been reported elsewhere for pit mound pairs. So over time, the mound gets smaller because it erodes away, and the pit would get smaller because it would be filling in. And this is where we're getting to age dating and radionuclides. So this is kind of what I brought to the table. I showed up in an NSF EAR postdoc where I had some funding to do cross-site work, and got a hold of these pit mound samples and was really intrigued by this story. So I went back to archive material from what was collected in 2010 and analyzed it for short-term fallout radionuclides, focusing on lead-210 and cesium-137. So these relatively short-term fallout radionuclides are delivered to the Earth's surface in precipitation and all have rather strong particle affinities. So they're used quite often to be tracers of erosion or used in sediment fingerprinting exercises where you're trying to source suspended sediment into a channel to potential hill slope sources on a storm event timescale. They rather strongly sorb to particles, and their primary disappearance from that particle sorbed complex is by radioactive decay. So this can be accounted for by knowing the half-life and the disintegration constant. There's 3 short-lived fallout radionuclides that are used a lot in terms of event scale to decadal scale timing of processes. And that would be beryllium-7, which has a 54-day half-life. We did not use that here. Lead-210, which has approximately 22-year half-life. And a portion of your total lead-210 comes from the radon gas escape that would further decay in the atmosphere and come down in rainfall. And that's what we'll be looking at here, as opposed to that produced geologically. So you actually measure both and do a subtraction. We can get into this more. You're looking at me because I know you guys are interested in this. Cesium-137, which has approximately a 30-year half-life. We'll talk about that a bit more on the next slide. And I know in Shale Hills, Nikki West used a lot of beryllium-10 data, which is not short-term, but also a fallout radionuclide. And it has about a 1.3 million year half-life. And so some of the uses of these isotopes are the same, but I, as a hydrologist interested in events and short time scales, focus on the top 3. And here in Shale Hills, the middle 2. So as these are delivered in rainfall, actually all 3 of these, what tends to happen is they concentrate near the surface and become less and less, and their profile will go to 0 with depth. So if you have inputs and you don't have mixing and you don't have a ton of erosion that would continually excavate the top of your profile, the reference condition would be to have an exponential decrease in that profile with depth. So focusing a little bit more on cesium-137 and lead, I already mentioned cesium-137 is from atomic weapons testing. The peak of deposition in this area was really right around 1963, so it came in probably about 1963 plus or minus 5 years, but that's when the bulk of the deposition is dated to having occurring. It highly sorbs to particles. Like the manganese discussion we had earlier, and a relatively undisturbed profile, it provides another event horizon of where your surface was during atomic weapons testing. And there's ways that you can look at where that cesium-137 peak is as an event horizon in the soil, but also look at the total inventory of cesium-137 throughout your core and compare that to what is known to have come in during atomic weapons testing to look for net gain or loss. So loss to groundwater. So with cesium-137, it has a really high binding affinity for clays. I actually was first introduced to it in grad school, where we were using it experimentally to sorb onto clays to track colloid movement. So its binding to illite is pretty irreversible. However, in places like shale hills, the concern would be downward colloid migration throughout the profile. So there are places and locations where you'll see a cesium-137 peak at the surface and maybe a separate sort of peak at the subsurface that would correspond with like a BT horizon in the soil where you would have some deposition of some fine particles. So the mobilization is often associated with fine particles rather than absorption, desorption of the cesium. Let's see, in the lead-210 excess, we've covered this. So there's geogenic lead-210 in this excess portion of lead-210, and you're able to compute the excess portion, and that's what we're looking at as having come in from rain. This also highly sorbs to particles. I actually have a master's student who's finishing up his data analysis from doing sorption isotherms of lead and beryllium onto different stream sediments to get their tagging conditions. So looking at these profiles, there's a literature around interpreting them. And what I'm showing here is some of my data from Christina Cesio, because it sets up this dichotomy nicely of interpreting a cesium-137 profile very shallowly in the top 15 centimeters of the soil profile there. So the green line here is showing a forest profile where we have maybe a little bit of soil growth since a peak around 1963, which here we're interpreting as 5 centimeters down, and then we have a pretty exponential decline to 0 in our cesium concentration with depth. The brown line is very characteristic of what happens in a tilled agricultural field. And so that cesium that's resident there gets kind of smeared within the plow layer because the plow continually mixes the upper several centimeters of soil. And additionally, the tilled ag fields usually undergo erosion as well. So the total inventory would be less, but the profile is very different. And as a punchline, this whole collaboration with Sue and I between this started because we have a mound profile that looks like a tilled ag field in cesium-137. Gamma ray spectroscopy is how I analyze the lead-210 and the cesium-137, and each sample is counted for 48 hours within my lab. So analysis time is long for several samples and many cores. The other issue to talk about with cesium-137 is it came in 1963 and it has a 30-year half-life, so it's going away. Unless you're near the fallout zone of Fukushima or Chernobyl or something else happens that we unfortunately, could occur. So what we see for these profiles with cesium-137 and lead-210 excess with depth, the cesium-137 is showed in the orange and the lead-210 in blue, along the south planar transect. So from the ridgetop to the mid-slope and the valley floor positions, we're usually seeing for the lead-210 excess that exponential decay curve that we expect if we have the fallout high in the top and decreasing with depth. And then we're seeing the cesium-137 peak is very, very near the surface, indicating that we don't think we've had a lot of deposition on top of what would have been an event horizon in the past 40 years. And then it also declines with depth. And it's very shallow. So we're talking within the top 10 centimeters of soils within shale hills. So when I went back and took my cores in those locations, I actually sectioned at 2 centimeter intervals to be able to capture these profiles. Let's see. So when we look at what's happening with these profiles in the mound pairs, we can see, first of all, we'll notice the Xscale, particularly when we're looking at the mid-slope, which is a reference position for cesium-137 inventory. Its inventory equals what it should have gotten with fallout. Our Xscales are way lower when we're looking at what's in the mound pairs. And in fact, I had to plot them separately because if not, it looks like they're right along the y-axis. with depth. So we have a less variable with depth profile on these, on both the old mound and the new mound. The cesium on the old mound is measurable. These numbers are above detect, and it is relatively low, relatively homogeneous through the top 25 centimeters of the profile. So this whole project started, Sue, because I plotted this up and it looked like a Tildak field. And I said, what's going on in these mounds? They really look like they're totally and completely mixed to me. And so, hence I'm here in this whole conversation. With the new mound, what's happened is I got this data a bit later, and they plot along the 0 line. And if anyone's really interested in the nitty-gritty methods, we can talk about it later, because they're below detect. My minimum detectable activity is above 0, and the numbers I was getting for the new mound were between 0 and the minimum detect activity. This is likely due to decay since it's input. So of our first hypothesis, based on both the tau plots and the fallout radionuclide plots, we're pretty sure there's mixing going on in the tree mounds. And so we think that no, our first hypothesis is a no. They do, in fact, disrupt soil profiles. So if we now look at homogenizing soil profiles and what's going on with these depth depletion curves to evaluate hypothesis number 2. And this really gets into how much of the catchment area should we see this over. So remember, we talked about numbers to keep in mind. Here's more with specifics about shale hills. There's over 2,000 large trees in the catchment. There's over 400 pit mound pairs based on some of Tim White and Ashley Deer's work. And these are pit mound pairs where they think the trees have fallen in about at least the last 70 years. We'll get to a timeline later that again kind of puts some lower bounds on this. So there could be more pits and mounds that weren't even picked up in this 467 number, especially if we're going to match the Gabay et al. Estimate of pit mound pairs covering 40% of the landscape surface in northern temperate forests. So there should be a significant portion, i.e. up to 40% of the landscape at shale hills affected by pit mound pairs over some time scale. But of the chemical depletion profiles, only 1 of 35, or 3%, accounted for homogenization that we're seeing happening in the profiles. So again, how do we reconcile this? The first thing we're doing is that we're saying, yes, tree throw does homogenize profiles, but we think it affects more than a small fraction of the catchment area. So we should be seeing more homogenized profiles. So we're actually saying no to hypothesis 2. Which brings us to what kind of my personal favorite is right now in thinking about time, right? So we have hydrologists and plant physiologists and geologists all in the same room, and time is one of those things that everyone trying to get their head around what is short-term, what is long-term, seems to be a really rich conversation. And so here's our chemical take based on these profiles of what we think the timing of some of these cycles are. In particular, we want to know if the time it takes to develop a depletion profile is less than the reoccurrence interval of a tree throw at a given location. So throughout this section, we're going to keep coming back to a timeline, and what we're going to be doing is adding more information onto this timeline to start narrowing the window when we think these things could happen. So first, how long have these 2 tree mounds really been there? So we can look at a history of manganese enrichment found in the surface below the mounds that we talked about from Beth Herndon's work. I know from talking with Dave in the 1930s, shale hills was clear cut. And this was an early 20th century clear cut where they dragged all of the logs out of there using animals. And so there's a chance that that could have influenced the tree age available in shale hills to a big extent, and also could have kind of evened out any pit mound topography that would have existed before that forestry activity. We have 1954 to 1968, surrounding 1963 atomic weapons testing, which can give us that cesium-137 deposition in an event horizon, and then up to 2010 when they were sampled. So that manganese being really enriched below the surface of the mounds and knowing about the clear cut is kind of putting us at least this side of the 1930s. The ages of pits and mounds were determined in the field by kind of a biological method, looking at whether or not the tree trunk was present in decay and what kind of the decay class would have been if the trunk was there. So the new pit and mound, the tree trunk was still visible in 2010, but hollowed out and in fragments, small indication of root plate. And so there's some classifications around how to interpret that information. And in the field, the observation was putting it at 40 years old. The old pit and mound pair was well-defined pit and mound microtopography with no evidence of a remaining tree trunk. So by this classification scheme, it had to have been older than 40 years. Due to they talked about the presence of the manganese enrichment layer that we covered. And Lin Ma was arguing that such enrichment occurred because of atmospheric deposition between 1850 and 1920, so post-industrialization. They're thinking the tree died somewhere after 1920, and that would also be consistent with it having died sometime after 1930 when that clear cut occurred. So they use that as the upper bound for 40 to 90-year-old of the age of the old pit mound. Pardon? It could have formed before the clear cut. That would be one possible explanation, but I am slightly skeptical given how they would have removed the trees with the forestry practices at that part. So it could have formed and it could have been missed by kind of the soil raising for them to drag the trees out. We can debate that. It's nowhere near the levels of precision forestry that happen with today's forest management practices. You know, I would have expected a lot more soil homogenization based on the timber extraction practices in the earlier 20th century. Also, when we look at the soil carbon content and the carbon profiles across with depth through the different mounds, we see the undisturbed mounds in the squares having really high carbon at the surface and showing an exponential decline with depth. Oh, sorry, the undisturbed reference for the mounds. The undisturbed mounds having, again, this exponential profile that we saw in the undisturbed reference for the fallout radionuclides. However, the older mound has very low and relatively homogeneous organic carbon content. The new mound has slightly higher, still slightly higher than the old mound, relatively homogeneous, but has this bulge here, an increase with depth around the rooting. And when Sue and I were talking, we were thinking it might take about 100 years for a carbon profile to kind of reset to look like an undisturbed profile. Yeah.
So, but the carbon profiles are maybe a little bit different than all the other elemental profiles that you're being supplied above, or you're being supplied above, or from using recycling and trees together, aluminum and calcium.
Right, so the aluminum and calcium will be supplied from below with the bedrock, and they're getting less and less towards the surface because of erosion leaving them. The carbon could be coming in from the top unless you're dealing with rooting layer. Dave talk about roots. But that decline from the surface, so the shape of that carbon profile is analogous to the shape of the fallout radionuclide profiles as well in a reference location, because those are also supplied from above. So we have these profiles of different chemical markers supplied from above that all have a really high surface layer and then exponentially declining with depth.
Carbon profiles usually look like that. Basically, because the source is from the surface. Yeah. But I never really understood because there is some, correlation to organic matter and
developing that profile fast because they're just
Collecting leaves. Mhm. Yeah. Well, the pits could be developing that, and you are starting to see some of that in the pits. It's talking about the mounds. So we're not seeing a return to undisturbed profile developing in the mounds based on the time scale of this. And we were kind of thinking, if this bulge here might be some sort of indicator of where the surface was underneath the bottom of the mound, like a buried A horizon. So if you're talking about streams walking through Pennsylvania, you talk about buried A horizons in your stream banks. Is it an analogous situation in your pit mound situation? Take longer.
Right, so if you look at the undisturbed top, which is squares, the old pit has already gotten itself back to looking like reference soil. But
The new pit's way overachieving.
So, but that's not the story of the mound at all. The mound is not back to the
Exactly what you just said. And so what I would need to do based on what you just said, I'm trying to stack all these different chemical lines up against our timeline, right? And so if we talked about soil carbon profiles taking about 100 years, that would give us a lower bound. But if a mound is going to take longer because it would shed leaf deposition more than collect it, then that, I would have to extend it that way. Right. Yeah. And then also putting the more tree-based dendro methods, so the tree decay class methods on here. That's giving us kind of this range where we're greater than 40 years of decay for the old mound and approximately 40 years for the new mound. The other thing to consider is that we would expect erosion to occur as the mound gets older, right? And so we looked at the size of the mound. Initially, the old mound was much smaller than the new mound. The cesium-137 inventory can be an indicator that erosion has occurred out of the profile in the mound since 1963. And so if we calculate the inventories across the three south planar mid-slope positions, or the three south planar hill slope positions, with that mid-slope being in the sweet spot where it would have the activity in 1963 of estimated fallout. At the time that I normalized all my counting to in 2013, I got the top row of inventory, which I then projected backwards using the radioactive decay or the disintegration constant to see how much activity in 1963 would that represent, and compare that to what the estimated fallout is from IAEA over this part of the world. And we see that the south planar mid-slope falls in the middle of this range, so we're using that as kind of a reference profile again here. And the old mound is you know, half or slightly over half of that, so indicating this experienced erosion. Yeah.
Surprising that you have lower, surprising that you have lower inventories in the ridgetop pit than on the mid-slope pit?
No, because I would assume that erosion could have occurred off of the ridgetop since 1963. And so
Like a road, I guess because yeah.
yeah. I assumed the loss of inventory from the ridgetop pit was due to erosion from the ridgetop position as part of the creep moving down. The one that surprised me more was that the valley floor is lower. Right.
And I'm thinking of like, you know, the sediment transport being proportional to the slope is going to be probably the highest possibility of preservation is going to be right on the ridge.
Well, the ridge top position, these are based on like the Li Xin-Jin setup positions. The ridge top is, it's not right specifically on the ridge top, right? It's slightly down. It's high on the slope though. And so for me, that the mid slope appeared to have an inventory consistent with fallout meant it wasn't net eroding. It was probably having some erosion and some deposition from what was coming down slope above it. So that the inventory on a net was in the amount of fallout.
The valley floors that losing material.
This is the one I'm not sure about. The swale tells a different story. When I plot up the swale transect, I was surprised that the valley floor appeared to be losing that much material. Either it's losing it to the stream or there was more down profile migration that I didn't get that low because it zeroed out before I hit that low. That's the biggest head scratcher to me. There's also this mechanism by which, so we'll skip to the bottom of this. This is a bit about the mobilization of cesium within profiles. It does, the highlights are, it can bind very strongly and be associated with clays. Plants can cycle it. So this could be something that would be going on in the valley floor position. Plants will cycle cesium as if it's potassium. And so with the half-life being approximately 30 years, that's long enough to see cycling where it's taken up through the roots and ending up in the leaves. So if leaves were falling that were then, the leaves were moving down slope as opposed to building up a duff layer, right, where it's collected, that would be one explanation. Or if it's in the duff layer that was removed, because when you take a soil core, you brush off the duff, right? If it was in the duff layer, it wouldn't be represented in that total inventory.
Can you measure cesium well in leaves?
You have to kind of grind up the leaves, and you would measure them the same way that you would measure it in the soil. It's a possibility. Where I've done this elsewhere with beryllium-7, for example, I've kept the grass layer, if it's in a field, and kind of dried it up and condensed it down and counted the grass and been able to get an activity on it per mass of vegetation overlying it. I don't know if I ever calculated it out for cesium. That was supposed to be one of Ralph Alto's students that did that. I can go back and look. Yeah. Yeah. So I don't know the specific answer to your question, but I know that this is something like the plant cycling as well as partitioning with through fall and canopy interception that has been studied quite a bit in the past 5 years in the areas around Fukushima. So they were getting very large inventories coming through in rain and wanting to know what was happening. So I don't have the numbers in my head, but if it's something you're really interested in, I could point you in the direction of some literature on that. Those orders of magnitude are just way, way higher than anything you'd see in Pennsylvania right now. Anyways. So what we were interpreting, to start wrapping this up, is that this old mound, we narrowed the window on the dating of the old mound based on having this mixed cesium profile. And we were interpreting this mixed cesium profile to mean that that mound existed prior to the cesium fallout with atomic weapons testing, and that the mixing was happening rapidly in the mound due to both the kind of smeared low and homogeneous cesium-137 profile, and also when we look at the lead-210 that keeps coming in with rain, that is also much more homogeneous than it is in the reference. So then we wanted to know, okay, we've kind of feel good about the dates of how old these mounds are that existed, but what is the time it takes to, or how do we evaluate the time it takes to develop a depletion profile? And is this less than the reoccurrence interval for tree throw at a given location? So again, this is really fresh. Sue and I have been going back and forth on this as recently as earlier today. And our kind of interpretation of this way the system is going, and we'd like to get your thoughts on this, is we have kind of several observations looking at the transformation of chemical profiles occurring on the order of decades following tree fall. So we have very few rocks on the surface that aren't associated with fresh tree throw. Erosion is occurring from the mounds over time, and we get that both from kind of measured volume estimates of the mound, and then the cesium-137 loss from the old mound corroborates that. We're thinking that the rocks are weathering within the mounds, and so we see less rock fragments over time. So for example, there were more rock fragments or a higher proportion when we look at the grain size distributions of rock fragments in the new mound than the old mound. So the old mound has about 35% rock fragments at surface to 80% at depth. The new mound varies from about 22% at surface to 32% at depth. We're inferring that rock fragments and sand, so those coarser particles, are disaggregating to silt and clay, and the silt and clay are then part of what's leaving and eroding out of the mounds. This weathering within the mounds is also leading to subsequent loss of magnesium, potassium, aluminum, etc. So those elements that we were looking at in the depletion profile. As the rocks brought up to the surface because of the tree throw are weathering, perhaps at an accelerated rate now that they're at the surface and in contact with the atmosphere, they would be losing these elements, and eventually a chemical depletion profile will again develop in the mounds. And so kind of putting the chemical depletion profiles, the short-term radioisotope profiles, and the carbon profiles, aligning them side by side and drawing horizontal lines where we're interpreting that bottom of the mound original land surface to be. You know, we could look at these and debate back and forth if it looks like the old mound is starting to pull more to the left on the tau plot and starting to develop more of a depletion profile as opposed to the new mound with time. We could do something similar looking at the lead-210 profile. Are we starting to get more exponential, meaning the structure of that mound is keeping what comes in with the rainfall more at the surface? So we're interpreting the movement toward the chemical profile of a reference site is occurring over decades, but we're not there all the way there yet. And so somewhere on this time scale of decades, we're starting to see the chemical profiles shift within these mounds. And so our thoughts on hypothesis 3 are quite possibly the time it takes to develop a depletion profile is less than the reoccurrence interval for a tree throw, particularly if the tree throw reoccurrence interval is on the order of more than 100 years. And that is as far as we got in evaluating our hypothesis since I landed at midnight on Tuesday night. But I have to end with this woodcut. So I've been thinking about this tree mound, like one cesium-137 profile has permeated into my brain enough that I purchased art. This is a woodcut by a local artist in the Twin Cities, Emily Kohler, and she calls it Morning After. And I was walking around this art fair in St. Paul, and she has all these beautiful kind of environmental scape woodcuts, and she had one left that's this picture of a tree that's turned over with the root wad up here. Pardon? This was her last one. And it has no pit, right? I know I have whole other issues with her interpretation of an aquifer system, but we didn't go there at the art fair. And this is what's hanging on my office wall next to my laptop monitor that I plug into every day. So I am reminded of that. So science spurs the art economy. Can put that in your broader impacts. art purchase. So I have to thank lots of people, NSF for providing funding to Shale Hills. I had an NSF postdoc that facilitated my coming up here and getting the profile that's stuck in my head. Jim Pizzuno was my postdoc advisor at the University of Delaware. He let me take over and play a lot with his gamma counters to measure these isotopes. My startup at UMN at University of Minnesota let me get at least one of my own to work with and play with. The CZO tree workshop provided some further thinking on this. The tree class that collected chemical data, everyone here at Shale Hills. So thank you. Questions and discussion. More questions and discussion. As I say, and there's absolutely no clock in here.
If anyone's listening.
Okay, I don't think this. I don't know. But you didn't have to do a profile in the pit itself, did you? Was it just on the mound? Or?
So there are some chemical profiles in the pits, I think, from the class. I didn't do the isotopes in them.
Okay.
I could. So one, you know, you can always do more. And Sue's trying to pull me out of the but one more set of data mode. So I think the carbon was in here, but I don't think we put tau plots in here.
Because the only thing I can think of is that, you know, the mound would be slightly more well drained, perhaps, than the pit, for example. So you might have like longer residence times of the water in the pit. So you could like compare and contrast the two profiles, you know, formed at the same time, but have slightly different like microclimates.
Mm-hmm.
You have that data. I'm not sure why we didn't want it this time.
Mm-hmm.
I thought.
Yeah, and I came across one other paper with the fallout radioisotopes where they looked at lead-210 profiles in a couple of pits, and they were trying to look at coming in since the pit was formed.
I know.
Oh no, she probably does. Oh. Of the population of the mounds. Well, statistically, we haven't sampled 100 mounds to be able to bound the confidence interval. Right. Yeah, no, right. So, of the broader class. So it would be to walk around and look at how many pit mounds would you see that have, so take, for example, the new mound that would have a tree in that decay class, for example, or that might be in a similar slope position, right? So thinking about the representativeness that way. And to me, these really represent vignettes, right? We haven't, like we could go from here and go up to, okay, if this many fell by this time and really try and extrapolate up based on that. But I think what we're trying to do is give a vignette of a story where we're looking at multiple different chemical profiles and they're starting to sort of converge on each other for what's going on in these cases. The one that I marked up or not?
So I have a question about the idea. So you had one of your intro slides. You talked about the hypothesis that if you go away from a tree, you know, because we're sampling away from trees, you see the depletion profiles, but that might not be the case everywhere. And I guess I'm curious if you could take advantage of the recent tree throws where you've actually brought up the entire profile from bedrock to surface underneath the tree and pick out in situ to do a profile, you know, that's now turned sideways. So
this way.
Back and see if you have a clean depletion profile right underneath the tree, or if it's being actively mixed, you know, during tree growth.
Hang on, can I try? Because I think I've thought about doing that, right? So when you get, so you would have to, hang on. So if this is your tree. Oh. I was going to use it as a prop. Way back. Yeah, if you core that way. Going that way. Yeah. So you, well, I mean, you could. Well, it seems easier to know where the bottom is than when the tree is already in the ground. No, so I've done this. I think you could, so I've push cored into stream banks, right? Where I've gone into a stream bank laterally. So to kind of treat it like that, although this has got more coarse material in it than the stream banks I was push coring. But the other thing to look at would be not just how the depletion profiles or the chemical profiles change, but I wonder if some indication of mixing could be if you could get a bulk density profile going through the mound that way and compare it to a bulk density profile. You know, a reference bulk density profile. Clean. See.
I mean, some of these trees are roughly 100 years old.
Mm-hmm.
And you could potentially get some interesting insight. Directly underneath the trunk, there may not be many fibers. There may not be many pretty voids. You might get a 2-inch core pretty far in.
Pretty far in.
And it would be interesting because it is fundamental assumption that soil in that place is, you know, similar to the soil away from the trees.
Yeah. Right. Well, and so concurrent with that thinking, in Christina, when we were sampling to try and get beryllium-10 profiles, so the long-term fallout radionuclide, right? We were actually looking in southeastern Pennsylvania for areas where Penn oak trees had just fallen over or died, because those are the oaks that were in Pennsylvania present when William Penn was here. And so we were thinking if we were right underneath the main part of the trunk of that tree, that should be a profile that's been relatively stable over a few hundred years if the tree had just come up. So it's a similar thing to try, not what's on the fringe out of the roots, but going right into the center. How old the tree was. Yeah. Mm-hmm. We're coring everything now. Wednesday.
And then is interested in working on it because it's already started.
But even things like your manganese profile, all the different profiles, the trees are covered, it could be interesting.
Well, and if the trees are about 100 years old. Yeah.
I mean, wouldn't we also want to analyze the roots in here? Like, it seems like that's interesting too. You know, like, what is that? Whatever core you can get out of there, what, you know, how much root is in there? How much soil is gone?
The soil there is much affected by like tree process, tree root process, like exudes organic acids. So I guess my question would be like, how, when you compare the two, what are you, if you look at this soil profile versus a soil profile without roots at all, the soil here will be very much influenced by, like the chemistry will be very different and influenced by
the chemistry in the mound,
yeah,
in general, would be influenced by the roots. But where would you be in shale hills not influenced by roots?
Yeah. So the idea is
right.
More fine roots underneath the tree is, I think, probably wrong. They're probably less. And once you get out into the more edge of that clay, you're not going to find any consistent relation. You find roots there, and halfway through the next tree, the root densities aren't going to vary.
So you're saying the stuff right under the tree
Well, I don't know about chemically. I know the roots because there's no, it'll be dry a lot. It's just, there's not going to be, you often don't find as many fine roots. First thing, with the roots so thick, they have a hard time putting out. They really have to be structural.
Well, if they're not a lot of fine roots, if there's mostly thick roots,
Right.
which I think are structural roots, because my
Right.
friend taught me that, then there'd be less chemical interaction.
That's the assumption, right?
From the root exudate.
Okay, but I asked you if there'd be less chemical effect on the tree. You said
Well, I don't know that in the context of from the roots, but there might be other chemical interactions.
So there'd be less chemical effects on the roots on the tree.
Yeah.
But there might be other things.
Right. So things like the water moving down the trunk could be pretty chemical.
The macropore space that created by large.
Yeah, so you're looking at all the processes involved, but certainly the
The stem flow?
Stem flow.
Mm-hmm. Well, that, yeah, so that would chemically change things like carbon coming in if it's DOC in stem flow. Oh, maybe. I'm trying. Sorry. Okay, this one. Yeah.
Then you've got, roots and fungi on either side that are in the soil that's quote normal soil, normal treated soil. And all of a sudden over here is this zone that's all mixed up. So they maybe are at a, shallow depth and there's no calcium, but then all of a sudden there's calcium. So now when you go to the one where we lined all the profiles up and we put the land surface on there. I mean, is that a viable idea? Is that a testable idea? Like,
How does that work with the mound of roots going along the subsurface and shooting up into the?
yeah, it's not really lateral in my idealistic worldview. But I mean, when the mound gets tipped up, there's roots in there, but they're no longer alive, right?
They're not going to stay alive, right?
Okay, there seem to be dead roots. And then, so there's a period of time where there's no living roots in there. And how soon will it be that living roots will get into that mound?
It's the encroachment hypothesis.
Well, like roughly, I mean, like.
It depends on the soil moisture relation in that mound. If we assume it has similar soil moisture relations to the bulk soil,
It's actually probably drier.
that's going to slow it down. So the nutrients aren't going to be very available.
But in a decade, would there be roots there in the mound?
Yes.
In a year?
Yes. If it's wet and then what?
A month?
No.
So between a month and a year. You gotta think like a
But
geologist.
they only be, 20 or 30 centimeters up, they may not be meters up. Because as soon as it starts to dry out, it's going to be viewed as unfavorable.
So can you explain how the carbon profile would go from the top profile to the bottom one? Like what happened to make it do that? Just like in words. So that I understand.
Carbon profile, that upper right-hand graph.
That's in the newer and the old.
Like let's say it started there and then 40 years later.
Yeah, and 40 centimeter depth line, you see that loop.
Well, it's going from the upper profile to the lower profile over time. So what's happening to make that happen?
So if at 40 centimeters, I buy the idea that it's a very old or very big.
Very day.
Now I ask you to think about it in a different way. That one, the top one, 40 years later, looks like the bottom one.
Would the nutrients from the buried A be taken?
Sure. Yeah, I mean, they're gonna be, what? Well, part of the carbon is being required, decomposed.
By bacteria. 'Cause there's
Yeah,
there's
why?
hardly any roots in there.
No, they're gonna, if that's an A horizon, very A horizon, which will proliferate. Because that's a nutrient rich horizon. We don't want to go to the B because it's pretty low fertility. But if it's a very A with a lot of nutrients, then the roots will proliferate in that horizon. And that would accelerate the microbial breakdown of that zone.
So minimum roots would get into that very A horizon, and it would accelerate the decomposition of that carbon. And it could
Well,
have,
I would say within a year, I mean, would start to do it. If it is truly a nutrient hotspot, that's quite excessive.
But so they could have started out with the same profile, but even the sort of original land surface profile has lost carbon as well because of respiration.
I got lost in that. I mean, what we're saying is that the tree homogenized the carbon in that upper profile, but it left the bump at 45, 70 years. That was the original.
But what I'm seeing here in the change from this to this, because this is getting deposition by leaves. This is getting increased mineralization because we have a lot of root activity in there that's going to bring the microbes and biological activity that will help break down that rich thing. So that's how I might interpret
So
that.
that's that hypothesis 4, in essence. I mean, that is hypothesis 4.
But if it is a nutrient-rich place, which would be a very big or very low, then there could be more roots growing into it. Just like your typical soil horizon has most of the roots in the top of the limit, so that's because there's most nutrients. But the roots are opportunistic.
They will grow wherever there's a high nutrient. So that's the argument is, gosh, can you go to the whole carbon profile? I mean, we're all three of them are there.
Hang on, I'm gonna see if I can navigate this way. I don't speak Windows.
Right here. We also have nitrogen, but.
Yeah, I didn't put it in here.
So, okay, so the idea is it started out like this, and then a tree grew on it, and then I don't know what happened to the carbon profile under the tree. You do, but I don't know.
Yeah, because no leaves could be deposited easily.
So it might be depleted in carbon under the tree compared to this undisturbed profile. That's possible. Okay. And then the tree falls over, and 40 years later, the carbon looks like this one. So it has a bump where the A horizon was, but mostly it kind of got mixed. So it got mixed, but there's still a bump where the A horizon was. And then 40 years later, it now is starting to look like this, which is the old mound. And what you're saying is it got mineralized.
And it could be also the kind of carbon. If it was a very it may have the type of carbon, wheat, litter and stuff that can be broken down a lot easier than say some of that fine particulate carbon that's very slow to decompose because it's also more healthy.
But regardless, whatever kind of carbon it is, the argument is it's getting mineralized because roots and fungal mycelia have grown in here.
That may be part of the reason, and part of the reason maybe it's just also more decomposable.
Okay, so it's more reactive because it was an A horizon. And
because it's
roots and fungi grow into it and mineralize it. And then it's starting to go back to essentially like this. Eventually it would look like this. It would take 100 years, and it might even take longer because it's a mound, right? So there's sort of a
Seems
top.
like it would be the time scale would be set by how that smooths back into the topography so that you can actually start collecting leaves on it.
Well, the 100-year time scale is if it were flat. Then there is a topographic effect too, so it might take longer than 100 years.
But if something starts growing up on the mound, be it herbaceous or be it woody.
Usually leaves that is the spot, kind of the very hay or low. Why you didn't see a chemical depletion there? If you've seen the bioactivity is
See, let's go back. The chemical depletion profiles. Yeah. Is that one of them? So the new mound. Oh, because this has the magnesium on it. Maybe. So the ones later didn't have the.
So that's fine, just leave it there so that I start this a little bit. So what you're saying, Jen, is why there is a depletion in there.
Right here.
If there really wasn't depleted, a depletion profile. Except it was under a tree, so then we'll document like it was under a tree, and it's not depleted.
The other thing, I guess, is,
Oh, but it
if
would.
that was where there was an acre, it starts out rich, right?
Because of the. Well.
But he's assuming that it's a depletion profile under the tree. And you're saying that maybe it isn't under the tree, maybe it isn't a depletion profile.
Well, the other thing is some of these nutrients might move faster. Potassium
It's more soluble.
a little bit easier.
Do you get enrichment of zirconium or titanium profile because they're not used by
These are all towns. These are all.
right, they're normalized.
Nice, zirconium.
I guess I'm talking about the absolute concentration of something like titanium or zirconium that we expect to enrich in a soil. And if you had a soil that was enriched in these immobile elements and then turned it over, you would be able to fingerprint that sort of overturned soil profile.
Well, I'm confused by what you're saying, because we are doing that. We do have an enrichment, and that's what the manganese is. It shows where the land is.
Okay. Oh, okay.
Anybody else have a question here?
I'll admit, I have absolutely no idea of what time it is up here.
I think
Okay.
it's great. I mean, we actually have I would think we have the core into it, don't you think?
Well, there's advantages if you have like one of the cores that you like a recovery probe, because then you'd be able to get bulk density as you're going too.
Yeah, I'm just thinking, dealing with the roots is problematic,
The
right?
roots and those big rock fragments.
Yeah.
Mm-hmm.
So I'm thinking you could maybe like just pick apart the rock fragments,
Take them off.
just pick them off one by one, and
Get
Mine 'em.
the rock fragments and then drill in.
yeah, I mean,
But that would.
I don't know what the easiest way to do that.
I mean, to me, this sounds really difficult, but I mean,
Get like a trowel and like scrape.
I think you could scrape it.
Yeah.
Like, I think you could pick your way in, but getting a real, like,
like an intact.
sample is a little bit hard, but I mean, maybe it's worth trying because it's an interesting idea.
I mean, I guess it is how it seems like if we're really just looking for a strong depletion profile, then you don't necessarily need to do like, I mean, just a yay or nay whether or not you have a depletion profile of.
Just get a sample as far in as you can, and then sample, yeah.
Mm-hmm.
Does that make sense, Ben? Try to get a sample as far in as you can.
Like pour in.
Now, the other thing that Diana was saying that
freeze
I
core
think
it?
is really interesting is, so, I don't know.
Here.
you could convince yourself that you're going from this to this.
Yeah.
You're starting to get this depletion profile
The
really
end.
fast. So what's happening to make it go that fast? Well, from what Jin Gu has done, about, for these elements, can you go to the other one? The one where I took some elements off. For the magnesium, potassium, and aluminum, those are pretty much an illite. And the way we think we're losing illite is about half is chemical and half is by little particles. We lose little tiny illite particles, even in the subsurface. And that one? No, the other one. You have the one with, oh, whatever. So the other piece of this is that we're losing rock fragments and we're losing illite particles. And so what happens to those rock fragments? You know, we don't see them when we're walking around at the surface. So what we're So what we're arguing, or at least thinking, is that the rock fragments actually decompose by losing illite particles. So that's actually what causes the depletion profile, but also causes the loss of rock fragments. Is the loss of these little illite particles.
Is there a way that you can look at like a particle
Yeah.
size analysis on a new and old mound and see if you're
She's got that in
So we had the grain size distributions in here, but that's the thing is, and we were talking a little bit about this. Those are sort of snapshot grain size distributions, right? So if your rock fragments are basically weathering, right? So your rock fragments get measured as a rock fragment. They're not necessarily eroding out as an entire rock fragment, right? So they could be generating more fine particles, while at the same time you're having erosion of what was fine particles.
Okay, so this is the new mounds, the old mounds,
Mhm.
depth 0 to 7, depth 0 to 7. This is the fraction in percent 0 to 100. This is rock fragments. So the new mound is almost like 45% rock fragments everywhere. The old mound is like 30%. And I'm a geologist, so I believe this is a representative sample of all the pits and mounds in the catchment. So I believe you can do what I'm now going to do. I'm arguing that it goes from 40% rock fragments to only whatever that is, 30% at the top, because the rock fragments are disintegrating into sand, silt, and clay. And what Jin is arguing is that the way those rock fragments disintegrate is they lose little particles of illite. And we can show that this is happening.
Well, an alternative explanation, one that came to my mind, is simply that it's a mound, so erosion is going to be much enhanced, and it's the fines that are going to erode a lot faster than the coarse.
But we see the decrease in the coarse.
The rock fragments should have become higher then, right? This is the old mound, this is the new mound. So the new mound is changing into this. That was perfect.
Purely erosion.
Yeah.
And the opposite of what you would see at Garner Run, walking around Garner Run, there are piles of stones at the foot of the tree row. It's because you do lose the fines and the coarse fragment gets the fine.
I mean, to me, almost the strongest argument, which we figured out like 2 hours ago,
yeah.
is that
Since lunch.
you see rock fragments coming up to those trees. We know they fall under the trees when you can still see the tree. But then when you walk around, you don't see rock fragments everywhere. So those rock fragments are disappearing pretty fast. Which is, I mean, I don't know, maybe there's some fallacy here, but I mean, this is very fast with these perfectly representative pit and mound pairs.
Dropped.
Well, it's 5 o'clock on Friday, I'm planning to stay tomorrow.
So I have to get out of town. Yes, thank you.